We're going to take a look at the natural logarithmic function now, which is very closely related to the natural exponential function. They're both base e. Remember, e is about 2.71828 and so on. So we define the natural logarithmic function, y equals log base e of x, if and only if e to the y is equal to x. So they are both base e, and there is a relationship, if you'll look, to get e to the y equals x, I can take my base e to the y and get x. So you can always go between different forms of this. Sometimes log base e is also written as y equal to ln of x, or the natural log. Still, e to the y equals x. Well, let's see what the function looks like. The exponential function basically is increasing and opens up, or decreasing and opens down. So since the log function base e is related to it, it should have a similar shape. Let's look at a few points. I think what I'll do, since I don't know offhand, say if I let x equal 1, what the natural log of 1 is, I'm going to use the exponential form. So I'm going to choose values for y. Say, let's do 0 and 1 to begin with. So if y is equal to 0, e to the 0 is 1, so x is 1 when y is 0. If y is 1, e to the 1 is e, which is about 2.7. So that's my x value when y is 1. Let's see what this looks like. So far, I have x equal to 1 and y equal to 0. And then I have x equal to 2.7, which is about 3, a little bit less than 3, and y is 1. So it's curving up like this, increasing, and as the y values get bigger, if y is 2, I have e squared, 2.7 squared, so the numbers are increasing gradually. But what happens down here, less than 1? Can I put in 0? If x is equal to 0, I would have e to some number equals 0. Well, it doesn't matter what you put in for your number, you're not going to get a 0 for x. Let's try letting the y value be negative 1 and see what we get. If y is negative 1, I have e to the negative 1. If you remember from your exponents, a negative power, we'll put that in the denominator as 1 over e to the first. 1 over e is about 1 over 2.7, would make it about a third. So if y is negative 1, my x is about a third. So it looks like that. So my graph actually will approach the y-axis, but it'll never cross it because there's never a way to get x equal to 0. So let's think about what the domain is. The x's that I can choose here are all positive numbers. I can never even have x equal to 0. So over here, I can't put in a 0. I can't have ln of 0. I can't have ln of a negative. But the y values will keep dropping. I can have any kind of negative y. I can have any kind of positive y as it continues. So my range is all real numbers. Well, let's look now at an example to see if there is some way that we can use our natural log formulas here. Let's say we have natural log of x plus 2 equals 3. And I want to solve for x. Well, x is not just inside a parenthesis, it's inside a parenthesis inside the logarithm. These are not multiplied, this is x inside a function. So I have to get it out of the function. And if you look up at your exponential form, I don't have an x inside a parenthesis or inside a function. It's just sitting out there all by itself. So what I want to do is take my logarithmic form and change it to the exponential form. If you need to write it as log base e of x plus 2 equals 3, then you can see that e to the third is equal to x plus 2. So it's sort of the roundabout, take the base to the other side of the power and back to that, which tells us that x is equal to e to the third minus 2. We're going to look at this example now that is a whole string of natural logs, so don't be afraid of it. We will have to go back and look at some of the properties of natural logs in order to solve this problem. One of the things that we have is that if you have the natural log of x equal to the natural log of y, we can assume that x is equal to y. So if we could get one natural log on this left side of the equation, we could actually eliminate the natural logs. But notice it's just ln. I have a 2 times ln right here, so that's going to require a rule for logarithms. The rule is one you've probably seen. If I have natural log of u to the r, what I can do is bring the r around front, and it's r ln of u. What we have to do now is go backwards. We have to take the 2 that's in front and make it become the exponent. So I have natural log of r minus 4 squared minus ln of 2r minus 3 equals ln of the big fraction. But we still don't have one natural log. But at least we just have ln minus ln. Now that brings up the next rule that we have to work with. The rule usually says natural log of u divided by v is equal to ln of u minus ln of v. Well, we have the minus, so what we're doing is starting on the right-hand side of the property and working backwards. So that since I have a log of something minus a log of something, I can write this with one natural log of the first part divided by the second part, so that I can compress them into one log. And then it equals the natural log on the other side. And then back up to the first property we looked at, I can eliminate the logs and just set the two fractions equal to each other. And then I'll have to cross multiply so that I have 21 times r minus 4 squared. R minus 4 squared, that's another one of those things you're supposed to remember. R minus 4 squared is actually r minus 4 times r minus 4. You can't just go r squared minus 16. So this would be r squared minus 8r plus 16 equals, and on the other side I'll have my 4r minus 17 and then multiplied by 2r minus 3. So we have to continue to multiply things out and then combine terms on one side. This side will be 21r squared minus 168r plus 16 times 21. 16 times 1 will be 16. 16 times 2 is 32, and 1 is 33. Pretty impressive, huh? equals over here 8r squared minus 12r minus 34r plus 51. And now I want to combine all my terms. So if I take my 8r squared and subtract over here, I'll have 13r squared. My negative 12, if you bring that over here first, or however you want to bring it over, what you end up with is a negative 122r. 12 and 34 is 46. Subtract from that. Plus 336 minus 51 gives me 285, and that's set equal to 0. And then I have to factor. So if I try to factor, this is really nasty. So is there anything I can pull out that's in common here? I don't think so. Okay. So when we're trying to factor this messy thing here, what you cannot do is bring the 285 over. It's a quadratic, and to factor, it has to be equal to 0. So let's see what we can think about this. 13 is prime. It's only 13 times 1, so we're very limited. We have to have 13r here. We have to have r here. This is a minus. This last term is a plus, so we have to multiply two negatives to get our positive. So both of these are negative. Now let's see if we can think what else is going to come out. People factor differently. If this is not the way you know how to factor, that's fine. But this is kind of a standard way that math people factor, so if you do have a different way, you're welcome to use it. The last factor has to be a product of these two numbers. So this 285, I know 5 divides into it, so I'll put it over here. So 5 divided in there, I'll get 5 into 28 is 5, 3 left over 57. And I can solve for this, and I'd get r equal to 57 over 13. I'd get r equal to 5. And those would be solutions. If the factoring, if I've lost you totally with the factoring, that's fine. That's why there's a quadratic formula based on ax squared plus bx plus c. So if we're solving, in this case, for r, it's this in place of the x. This is really r. Would be negative b plus or minus the square root of b squared minus 4ac all over 2a, where a would be the 13, b is negative 122, and c is 285, and that's not a problem. Now there's still an alternate version. When you get to the part where you've gotten rid of the logs back up here, if this were a multiple choice question, and you had, say, 4 answers, and one of them was r equal to 4, you could plug in r equal to 4 here, r equal to 4, r equal to 4, and see if you get the same thing on both sides. Now, r equal to 4 would not work here because 4 minus 4 gives you 0. This whole side would be 0. If r equals 4 here, you don't get 0. So then you would test the next value, and you would not have to actually go through the factoring or the quadratic formula. So that's something else you can do with a problem like this that starts off looking very complicated, but as you work your way through it, working backwards from your logarithm properties, this is something that you can do.